In this video, we're going to look at the next example and some definitions in section 12.1 and 12.3. All right, so first let's look at some definitions. So these definitions are going to help provide us with some methods for analyzing functions of two variables. So it says let z equal f of xy be a function of two variables, x and y, and let c be a constant. So one thing to note here is that you might say that, well, we see three variables, x, y, and z, but we're told it's a function of two variables. So meaning the inputs. So a function of two input variables. And those input variables are x and y, and the output is z. So often when we're talking about a function of something, those are the input. So to be more specific, you can put input there to help remind yourself. Just like when we see f of x equals y, we say this is a function of one variable. The input is x. Okay, so let's look at these three different methods, or rather two different methods, but we'll see them in context in three different parts of this example. Okay, so first, number one, it says the curves z equal f of c comma y and z equals f of x comma z are called cross sections of f. So geometrically, we get cross sections by intersecting the graph of f with planes x equals c and y equals c. So let's go ahead and unpack that a little bit. Recall c is a constant. So what that means is we're fixing some x value, and we're just looking at what happens to this function with that fixed x value. So we'll see this in an example, but I'll just draw a little sketch. So if we have our function f, so it's going to be some surface like this, meaning we have for any xy, our output is somewhere in the z direction. Okay, so this will be our graph f. And so if we fix some x equals z, my pen is making streaks, so let's just clean that up. All right, so if we fix some x, we'll call it c. So what we're doing then is we're only going to look at those input values where x is c. So we're only going to look at those values above this line, x equals c. Notice y could be over here, up here, anywhere along this line. So then what that looks like is a line in that surface, in that function of f. So it's as if we've taken kind of a slice out of that curve or of that surface. So we call that a cross section. We're going to see this a little better geometrically in these examples. Okay. But then the other idea we have, number two, is the curve C. So now fixing an output equals f of xy is called the contour or level curve of f. Geometrically, we get contours by intersecting the graph of f with a plane z equals c. So meaning we take our surface and we look at what are those x and y values that all occur at some fixed z value. And you might have seen this in a topological map where you see these curves that represent different elevations. Those are exactly contour curves or level curves. All right, so let's make a little bit more sense of this by looking at the next example. So in this example, we're told to let z equal the function f of xy equals y squared minus x squared. First, we're going to find the equations for the cross sections z equals f of 1/2 comma y, z equals f of x comma negative 1/2, and then the contour at z equals 0.3. And the pictures below are illustrating these curves. So we see that we have three pictures where we have the same function, this kind of saddle shape. This is the same function in each. Notice this one is just a little rotated from these two, but it's the same sort of Pringle chip or saddle shape. And actually in mathematics, these kind of shapes for a graph is called a saddle shape or a saddle. Similar to a parabola is a certain shaped graph. Saddle shape is one that we see here. Okay, so that's the graph that we see in these curves in this surface. And then what we're doing in this first picture is we're looking at when x is only equal to 1/2. So notice this is the x-axis. We see that x is 1/2. And so we're intersecting our curve with this slice, with a slice at, or that is cutting the x-axis at 1/2. And so when we look at this first part, so when we look at this cross section here, when x is 1/2, we're going to get the shape that's created when these two graphs, or when this plane and our graph intersect. So that's the shape that we're going to get. So let's see how that works algebraically, rather. And to do that, we're going to find those equations of the cross section. So here, for this first example, x is equal to 1/2. So what we're going to do is look at z equals f of 1/2 y. So notice our formula for our function is y squared minus x squared. So that would be y squared minus 1/2 squared. So that is just y squared minus, so 1/2 squared is 1/4, so y squared minus 1/4. So notice now that this equation is just in one variable. So we only have one variable here. So that means this is a curve. There's only one variable. We don't have two x and y inputs that we're using to find an output. We just have one variable giving us y. And so we can see that here, that this curve that we get is the same shape here. Can even describe it. The cross section is a parabola, and we notice that that y squared is positive, and we see that that y squared is facing up like this. So is an upward facing parabola. All right, and we can write that equation of that line as z equals y squared minus 1/2, or rather 1/4. And so notice along this curve, the x value is always 1/2, and then the y value varies. So here's the y value, and the output value is up here at z. All right, so let's continue looking at the cross section that we're asked to do in the next part. And so that is z equals f of x, comma, negative 1/2. So what I encourage you to do is go ahead and try to work out that equation on your own before continuing with the video. And then when we're ready, we'll look together. All right, so after you've had a chance to look at that on your own, let's work it out together. So we're looking at z equals f of x, comma, negative 1/2. So we're looking at when the y-axis is at negative 1/2. So that's being fixed there. So intersecting, looking at that plane that's defined by y equals negative 1/2. And we're going to look at that intersection of our curve with that plane. And maybe you can even see what kind of shape this is already coming out to be. All right, but let's figure it out algebraically. So we just plug in our values for y, negative 1/2 squared minus x squared. So that becomes 1/4 minus x squared. So we could write that as negative x squared plus 1/4. So notice that that variable is negative. So this is giving us a cross section that is a downward facing parabola. So we see it's a parabola because of that x squared term. And so here x can be anything along this x-axis. And then the output value are the z. So that's why we're getting just a curve there. So the equation for this curve is given to us by z equals negative x squared plus 1/4. So let's finish this example by looking at the contour when z equals 0.3. Change our color here. All right. So now we're looking at when z equals 0.3. So what this is telling us to do is determine those x and y points that evaluate to 0.3. So what we can do is plug in our formula for f. So recall that's y squared minus x squared. So we want those x and y points that give us 0.3 when we square and subtract those coordinates. So what kind of shape does this curve look like? Well, I encourage you to look at the diagram over here and see if you can maybe draw out what that curve looks like. Kind of hard because we have the underside of the saddle as well that we're looking at. So does this shape look familiar? So it might have been a while, but when we have an equation like this, where we're squaring and subtracting, this is actually a hyperbola. And you might have seen it before on an XY axis. It looks something like this. There's two parts here, like that. Or sometimes they're like this, just kind of depends on the type of parabola. And so here we see that shape appearing. There we have the both sides of that slice. So that equation is y squared minus x squared equals 0.3. And here too, we can see that what we've done is taken our graph of f and intersected it with this plane that's flat at z equals 0.3. And so that those orange curves that we get, those are called contours or a level curve because they're all level at z equals 0.3. All right, great work going through this example. And so please refer to this example to help yourself practice how we can analyze those functions of two variables. So just to summarize, the technique is to look at these cross sections by fixing an x or a y, and looking at contours or level curves by fixing an output z and determining the x and y points that give us that z value.